And so remember, just to recap, so we've already got this written down, don't need to write it down again. We're looking at this enzyme substrate reaction, and we've got 4 unknowns, that S, E, this we called C and P. So we wrote down 4 ODEs using the law of mass action. We then saw that one of them decoupled from the rest, so that left us with 3. And then we used conservation of enzyme to reduce it to 2 equations. We then non-dimensionalized, and we got to here. And then we said epsilon is very, very small. It's E naught over S naught. Remember, so it's very, very small. So just set it to be 0. And then we get this. And this contradicts the initial conditions. Okay? And the reason why we have a problem is that when we put this to be 0, then we've reduced this from a second order system to a first order system. But yet we've still got the 2 initial conditions. So it's overspecified, and therefore there can be problems with it. Okay? And then we ended up at the end of the last lecture saying that right at the beginning, dv by d tau looks like, this is 1, this is 0, so it looks like 1 over epsilon, which is very large. So even though epsilon is small, dv by d tau is very large. So you can't just put this to 0. So therefore what we need to do is, if this is going to change very fast, so we say v is changing rapidly at the start. So that means we should magnify, if v is changing very rapidly, we should magnify the time near the beginning so that we can see it better. Okay? So we need a new time scale. So tau was our old time scale, and now what we want to do is we want to magnify this for the new time scale. So to magnify something, you multiply it by a large thing. Okay? So at the moment, we don't have any large values here. We've only got a small value, epsilon. But how do we turn epsilon from being a small value into a large value? Turn it upside down. Multiply it by 1 over epsilon. And so that means in the time tau goes from 0 to epsilon, very, very narrow time, sigma will go from 0 to 1. So you can really see what happens. Okay? And so now we'll do this out sort of properly. Then we set u, which originally was a function of tau, and it depended on epsilon. That's now going to be some other function of sigma and epsilon. Okay? So now we're going to substitute that into that and get the equations in terms of du hat by d sigma. And if we do this out very quickly, du hat by d sigma will be du by d tau by d sigma, which is epsilon. So that means du hat by d sigma will be epsilon times the right-hand side plus but now what about this one? Now in this one, epsilon dv by d tau is just dv by d sigma. Equals u minus u plus k v. And we still have u hat at 0 equals 1, v hat at 0 equals 0. because this is the beginning. And now you see we've no epsilons here. That's the key thing. And then we look for solutions. Because this is fully non-linear and you can't solve it, we expand u hat and v hat, make sure I get the right notation here, as u naught sigma plus epsilon u1 sigma plus etc. So in other words, we look for a perturbation solution of this form here. So this would be epsilon squared, u2 hat sigma plus etc. And the same for v hat. So plugging that into that equation, we will get d by d sigma u hat, and now I'm going to sort of be a bit lazy and not put the sigmas in, plus etc., equals epsilon minus u hat minus u1 epsilon u hat plus etc., etc. Okay, just put them all in. And now what we do is we equate terms. So if we look at order epsilon to the 0, here we have d sigma by that, and on this side we have no term of order epsilon to the 0 because everything's multiplied by epsilon. So we have 0. Okay, and the reason why we have that is we're making the assumption that these are order 1 and therefore they can't be balanced by terms of order epsilon, because epsilon might be 10 to the minus 6. And we're assuming that all of these things are order 1. Okay? So we've got something of order 1, and we try to balance it with something of order epsilon. It doesn't work. So we have to do this. Okay? And that implies u naught hat is a constant, and the initial condition, well, u is hat is 1, and that implies that u naught is 1. Okay? Because the initial condition, put that actually at 0, that implies that u hat naught at 0 is 1. Again, by when that's 0, actually I should put that epsilon in, being a bit bad here. If that's 1, then it can only be balanced by this term. So this must be 1. It can't be balanced by these other terms. Okay? And then what about the other equation? D by d sigma v naught plus etc. equals u naught plus etc. minus u naught plus etc. plus k times v naught plus etc. Okay? And these should all be hats. Now let's look at order epsilon to the 0, and we get that equals u naught, and then this will be epsilon, so that doesn't count, minus this, and the rest of these will have epsilon in it. Okay? U naught hat equals 1. Therefore, this equals 1 minus 1 plus k v naught. So that's a linear first order ODE. You can either solve it by using integrating factor or by using complementary and particular solutions, and I'll leave it to you to show that you end up getting this thing here, where we've used the initial condition that v hat equals 1, and that implies v naught of naught. Sorry, that equals 0, and that implies that equals 0. Okay? Let's just check. When sigma is 0, 1 minus 1 is 0. Okay? So obviously when you integrate this up, I mean, you can see this doing it in your head. Bring that over to here. There'll be a solution e to the minus 1 plus kappa sigma. That'll be what's it called? The complementary solution. And then a particular solution would just be v naught equals 1 over 1 plus kappa. So the solution is going to be 1 over 1 plus k plus a times e to the minus that. Initial condition has to be 0, so the a has to be minus 1. Okay? And you can see that we could have got these solutions from just going to here and putting epsilon equal to 0. And now it's fine to put epsilon equal to 0 because that still leaves these as a second order equation. With the two initial conditions, that's fine. Okay? And now, can we understand what's going on here? U naught is approximately 1 in this initial time. So let's start plotting this. Eventually we'll want to plot it as a function of tau. So what's happening here as a function of sigma, sigma is t over tau over epsilon. So this is happening in a very small region here of order epsilon. And so what's happening here is that u is hardly changing. It'll decrease a little bit because du, there's a minus there, but it's roughly speaking 1. And what's v doing? V starts off at 1, at 0, and goes to 1 over 1 plus k. So as sigma gets very large, that'll go to 0, this will go to 1 over 1 plus k. Sigma very large means tau, if tau is about 1, sigma is 1 over epsilon, that's huge. So basically, v is going to go something like that. Okay, where this is about order 1. Okay? And meanwhile, u is going to stay sort of constant, like that, almost constant. And that's v. We can understand this mechanistically. If s is huge and e is very, very small initially, then when you interact with s, you don't use up much of s. Okay? So s is staying, roughly speaking, constant. And s we've transformed into u, so u is staying, roughly speaking, constant. Okay? But slowly and slowly, as you eat away at s, it's going to decrease. But that's on a long time scale. Okay? So now let's go back to this one. And now you might say, but that one didn't work. Why are you going back to it? Well, because a bit of magic happens now. Okay? Because remember, the initial conditions here were 0 and 1, and we couldn't match those because v, where did we have it? V, if u is 1, v should be 1 over 1 plus k. But now, what about trying to match it here? So here, u is approximately 1, and what's v at this point? Well, wouldn't it be great if v was 1 over 1 plus kappa? Well, what is it as sigma goes to infinity? It's 1 over 1 plus k. Kappa, I keep getting mixed up in kappa and k. So now this works. The thing we did yesterday works when we have these as the initial conditions. Okay. So by magic, this inner solution evolved to give us precisely the sort of conditions we need for what's called the outer solution. So if we do this properly, the way you do this properly is you would expand u of tau epsilon to be u naught of tau plus epsilon u1 of tau plus etc. V of tau epsilon to be v naught of tau plus epsilon v1 of tau plus etc. And then you'd substitute into those equations there, and then at order epsilon to the naught, you would get du naught by d tau equals minus u naught plus u naught plus k minus lambda v naught. And then we get 0 is u naught minus u naught plus k v naught. And now we have that as tau goes to 0, u equals 1. So it matches with the 1. And v equals 1 over 1 plus k. So it matches with the 1 over 1 plus k. Okay? And so if we do, so this tells us by doing the expansion that v naught, that u naught is 1 and v naught is 1 over 1 plus k. Okay? And so what, like we did yesterday, that gives v naught equals u naught over u naught plus k. And that's fine now. And then we've got du naught by d tau equals minus lambda u naught over u naught plus k. And you can integrate that up if you want. You get u of tau plus k log u naught of tau equals a minus lambda tau. And then the matching condition, so these are called matching conditions. Will imply, well, if you think about it, as tau goes to 0, this has to go to 1, This will go to 0 because that goes to 1. This will go to 0, so A must be 1. And so now we've got our solution. Okay? And so what they're going to look like is that's going to sort of decrease, and that's going to decrease. And they're going to go to 0. Okay? So this we call the outer solution. And this we call the inner solution. And this we call the matching condition. Okay? And this is called a singular perturbation problem. Okay? A regular perturbation problem would be the problem that when we put epsilon to be 0, we do not change the order of the equation. Okay? So we can think of this, if we just started out, if when we'd non-dimensionalized, we'd got this as our system, then we would have said that's a regular perturbation problem. Okay? Because you put epsilon to be 0, you don't change the order. But here, we do change the order, and that's called a singular perturbation. Okay? Now, crucially, in real life, if you're doing experiments, this rapid change might be on the order of 10 to the minus 6 seconds. So you won't see it. So in fact, all you will see will be this part. In other words, the bit that you will see will be the bit in which we do just put that to 0. Okay? And this is called the quasi-steady state assumption. QSSA, or it's sometimes called the pseudo-steady state hypothesis. PSSH. Okay? So in other words, after this initial very fast change, which occurs because this is 1 and this is 0, so dv by d tau is 1 over epsilon. What's happening is this is coming down because u is decreasing, and v is coming up because v is increasing. So after a while, this becomes small. So we are absolutely justified in putting that to be 0, because dv by d tau is no longer very large. Okay? And we call that a quasi-steady state assumption, because steady state would mean put that equal to 0, put that equal to 0. What we've done is put one of them equal to 0, and therefore we call it the quasi-steady state assumption. And what that's really telling us is that if I know u, then I can immediately find v. Okay? So that's what that's telling us. And so just some terminology. What we call this, so we've got here du by d tau is equal to minus ru. This is called the uptake function. In other words, it's the function that describes the rate at which we're taking up the enzyme, the substrate, okay? So what happens in real life? In real life, you don't go through and do all of this analysis. In real life, if you get down to here, then you just say, I now use the quasi-steady state assumption, and I just put that equal to 0. Okay? So you can imagine a situation now where we might have maybe 5 or 6 variables. And maybe all of them, except one, have epsilons, which are very small. Then we just say, use the quasi-state assumption, put zeros everywhere, get everything in terms of u, put it into there, and then we've got our equation to solve. Okay? And so if you, in the 4th year, do perturbation theory, that will do stuff like this, where you find a small parameter, and that means there's a separation of scales, of time scales. There's something happening on a slow time scale, something happening on a fast time scale. Okay? So the last thing I want to point out on this stuff is just another example of using the law of mass action. Suppose you have that. So law of mass action will give us, now that we call concentration A, dA by dt is minus K1 AX, because that's lost. And now this, how about that going back? We write this as x plus x. So the rate going backwards is x squared. So we get plus k minus 1 x squared. And what about dx by dt? Well, going in this direction, it's k1ax, but should that be a minus? Well, no, because this x has become 2x, so we've gained an x, so that's a plus. Going back in this direction, we had 2 x's, we've gone back to 1x, so we've lost x. So that's that with the squared. Okay? And this is called autocatalysis. Because X catalyzes its own production. Okay? So this is sort of example of using different scales, and it's an example of what's called model reduction. Because we started off with 4 ODEs to solve, and we ended up having only 1 ODE to solve. So we reduced the problem significantly. That's called model reduction. So we're now going on to another example. It's called neuronal signaling. And Hodgkin and Huxley and excitable kinetics. And this is in Jim Murray's book, Volume 1, Chapter 7, Section 7.5, but it's also on the notes. I put the notes up on the website. So the idea here is that when we nerve cells, so our brain is full of a huge number of neurons, and neurons signal to each other. And the way they signal to each other is by sending an electrical current. Okay? So this is a bit of background biology that you don't need to know. Okay? So I'm going to go through it very quickly. So nerve cells, which are called neurons, signal to each other. So if you want to do something, your brain has to send a signal to that part of your body to do something. And it does that by sending electrical currents. And these nerve cells, neurons, have axons. So basically, if here's your nerve cell, it's got this big long protrusion, which is called an axon. So it sends an electrical current along here, and then the next neuron is sitting here, and then it jumps across to the next one. And in that way it propagates. So some sort of signal goes like that and propagates. Okay? And nobody knew how this happened. So what Hodgkin and Huxley did was they said, consider the simpler case, the space clamped case. In other words, let's consider the case where it's not propagating, but it's just firing in time. And so basically the idea was this. That this is called voltage. This is the resting potential, voltage or potential. And this is called resting potential. Potential, can't spell potential. And the general idea is it's sitting nicely here, sleeping, and then gets a bit of a kick. And what does it do? It goes up and comes down like that. And that's the signal. And that's called firing. Okay? And so the question is, how do you get that? Okay? And that's called an action potential, because some action happened. Okay? So it makes sense. Resting potential, nothing happening. Action potential, something happens. And so the question is, how does that happen? So Hodgkin and Huxley wrote down a mathematical model for this in which they made certain hypotheses about the electrical activity of the axon that gave rise to this. They made hypotheses, these were validated, and in 1963 they won the Nobel Prize for medicine for doing it. Okay? And the two papers they wrote that were Nobel Prize winning papers, I think each one is roughly speaking 6 or 7 pages long. And the way they did it, now this is some more biology you don't need to understand. The change in voltage gives you current, where C is capacitance. Can't spell that. Okay, and the current is current that comes from this voltage. So the change in voltage causes a current, and plus if there are other currents. But again, sorry, that should be I. Don't need to understand this. And so what they did was they said, in their model, key chemicals, potassium, which is called K, you should remember from school, sodium, which is called Na. And so as the ions from these move, that gives you current. And then there's a pile of other currents that they just called leakage currents. Called L. And then they wrote down a mathematical model where they said that the current due to potassium was some constant times m cubed h v minus vn, where this is a constant. Ik. Let's write these down first and then say what they mean. Where that's a constant, and that's a constant. And IL, it's not the same constants, they're just constants, is GL V minus VL. So GNA, GKGL are called conductances, constants, and VNA, VK, VL are constants. Okay. What are these? What they proposed was that these ions moved through gates. And this is the probability that the gate would be open. So they said there must be 3 gates of this type and 1 gate of that type for sodium. So the probability that all those gates are open is m cubed h. There must be 4 gates for potassium. The probability of one of them being open is n, so the probability that all 4 open is n to the 4. So in other words, MNH, are probabilities, and they lie between 0 and 1. Okay? So think about it now. Plug these into there. So what do we have? We've got c dv by dt plus something times v minus vk plus something times v minus vl plus something times v minus n a. What is I? I is an applied current. We call that IA. That's called the applied current. Constant. That's a constant. Okay? So now if you look at this equation for V, it's a first order linear equation. Essentially dV by dt equals something times V minus a constant. And you can integrate that just like we integrated the one before by parts, by complementary functions, etc., etc. What could be simpler? Well, m, n, and h aren't constant. They depend on the voltage. There's a feedback. Unfortunately. And again, you don't need to know the biology of this. It's quite a complicated feedback. So the voltage determines whether these gates are open or closed. And you don't need to know the details of all of this. Basically, if you think about it, if M is open, 1 minus M is closed. So these are the closed gates, and then they're opened with this function. Opened gates get closed with this function. Similar for the other two. Okay, and they solved these numerically. Imagine solving these in 1952, when there's very little computing power. They solved these numerically, and they found action potentials. And they matched this to the squid giant axon. Okay, so the squid, you know what the squid is? It's the giant axon of the squid. Okay, so not the giant squid axon. It's the squid giant axon. Okay, so there's no giant squids here. It's just a giant axon. Okay. So then along came Fitzhugh-Nagumo. Well, that's two people. And they said, okay, there's 4 equations here. There's many different time scales, so we can use model reduction. We'll make some approximations. When we do all of that, we get functions that look horrendous, but some of them sort of look like this, and we'll just write down that as a cubic. Some of them look like this. We'll just write that as a straight line, and we'll see, by making all these approximations, can we still get this action potential business going on? So their model, and so again, you don't need to know the detail of how they reduced this model. All you need to know is they got this model. And V is related to voltage. Okay? So all of what I did here is just to say eventually you can get this model. Okay? So you don't need to have to remember any of the details of that. Okay, that's all background. This is the key thing here, where IA is a constant and f of v is v into a minus v, v minus 1, where a lies between v and 1. Okay? So that's much simpler now. So how do we solve this? Well, we can find steady states and do phase plane analysis, right? So I'll do the phase plane analysis. So we'll take the case IA equals 0. Let's plot the null lines. So we're going to have W equals f of v. That's going to be the v null line. This is a cubic that goes through 0, a, and 1. And it's minus v cubed, so it must look like this. So that's v dot equals 0. What about W null line? W equals 0 means dw by dt equals 0 means W is b over gamma times v. And so now you can see that's a straight line, and that straight line could just cross at this point, or could cross like this, or could touch here. So we're going to consider this case. Okay. If we're below here, W dot is positive. If we're above here, W dot is negative. Let's make sure we got that right. If W is enormous, this is negative, and therefore it must be negative above there. What about dV by d tau, V dot? Well, we could have that if V dot ends up being negative here, and V dot ends up being positive there. Is there a way we can see that? Let's see. Let's take V 0 and W non-zero. Then that's negative. So if it's negative for that point, it's negative for all points above it. Okay? And then we see we've got one steady state. And I leave you to do linear stability analysis and show that the steady state 0, 0 is linearly stable. So, suppose I start here. And I give a small kick. Okay, here they've sort of rejigged everything, translated everything, so the resting potential is now 0. Okay? So if I go to here, what's going to happen, V dot is positive, sorry, W dot is positive, V dot is negative, so I'll go here. I have to cross the W dot equals 0 line horizontally. Now V dot is negative, sorry, W dot is negative, and so I go down, and that's stable, so I go to there. Okay, so I did a little perturbation, and I went back to 0. What would happen if I perturb to here? Now V dot is positive, W dot is positive, but if it's because now this is positive, dV by d tau is enormous. dV by d tau is positive over epsilon, it's huge. So V will change very, very quickly. And W will change just a little bit. So we'll shoot along here very fast. Then we will cross this line, the V dot equals 0 line, have to cross that vertically. Now what do? Well, if we were to move away from that null line, then this would become a negative number, which would get bigger the further we moved away. Divide by epsilon, it's a huge negative number, which means V would decrease and would shoot right back to the null line. So in other words, we stay very close to the null line. Now we reach here, and we're loving the null line. We want to stay close to the null line, but we can't come down because W dot is positive. We have to keep up. So what do? We fall off. And now the same argument again. We fall off, and this divided by epsilon is huge. So this will go really fast across. W will increase a little bit across that horizontal. It'll decrease a little bit, go like that. And then, same argument, we go down like that. So what you see happened here is a small perturbation went back to where we started. For the larger perturbation, V increased very quickly, then slowly changed a little bit, then decreased very quickly, and then came back to rest. Exactly like this. Do perturbation, big increase, move for a while, big decrease, and then move back. Okay, so that's called a threshold phenomenon. Where A is the threshold, and we call this an excitable system. And now if you think about it, why do we need a threshold? Why is it important? Well, if there wasn't a threshold, then a minor change, a bit of noise, and your neurons would start to fire. You don't want that to happen. You want it to be mean, you want the neurons to mean to be fired. Okay? So, a household example of excitable system is the toilet. Not one of those flushing toilets that you wave to it, electrical one and it flushes, the one where you pull the thing down. Okay? Now if you pull that down a little bit, what happens, little bit of water trickles and you go back to where you started. Little bit. When you breach the threshold, then whoosh, huge change, water comes down, and then you settle back. Go beyond the threshold. Now imagine if your toilet was such that there wasn't that threshold. And maybe a fly lands on the flush and your toilet flushes. You don't want that. Your toilet be flushing all the time. You want your toilet to flush if a 10-kilogram fly lands on the flushing thing. And if that happens, then the least of your worries is having a flushing toilet because you've got a 10-kilogram giant fly in your bathroom. Right? So this is exactly what's happening here. Any little twitch, nothing happens. You have to really mean, so your brain really needs to say, Philip, give a stupid example, and then that propagates along, and then I start talking about giant flies. Okay? And at this point you're thinking, oh, I wish that A was much, much bigger. And that would have shut him up. Okay? So what we'll do the next time, because remember, we'll have our last lecture on Thursday at 9 o'clock, and that'll be in L2, is we'll do one more example of this, and then we'll get on to talk about a model for infectious diseases. Okay, so we'll do that next time.